Okay, so there are a few key terms you need to understand, and these are base and exponent. So if I gave you 6 squared, 6 would be the base, and 2 would be the exponent. And logs are all about exponents, and they answer problems that revolve around, let's say, 7 to the power n is equal to 49. Now we know n is 2, but you could also use logs. And for this, in your calculator, you would type log 7 and 49 equals n. Now leave this blank for now. But this translates as 7 is the base and 49 is my answer. So you're asking your calculator, 7 times something, that's the answer, this something bit, is equal to 49. And your calculator would of course then say log 7 49 is equal to 2, so therefore this something bit is 2. Similarly, if I gave you, let's say, log 2 8, you're asking your calculator 2 to the power something is equal to 8, because remember this 2 is your base and this 8 is your answer. And of course we know that this n is going to be 3. So as a final example, if I gave you a problem that went along the lines of 2 to the power n is equal to 16, in your calculator you would write log 2. So you're telling the calculator, right, listen, we're using a base of 2. So I've got a base of 2 and I want an answer of 16. So you're saying, what do I need to raise 2 by to get 16? And your calculator would give you an answer of 4. Which of course you might already know, but to be honest, when the numbers get higher, it's just easy to type into the calculator. Okay, so now that we've got that out of that way, it can be important and useful to learn 2 basic log rules. And the first one is that log a to the a equals 1. Now we can actually prove this. Remember, if we translate this into normal speech, this is asking the calculator a, because remember that is the base, a to the power something is equal to a, because remember this other a is your answer. N has to be 1. So this is quite a useful rule for reducing more complicated logarithms. The second is log base a of b to the power c equals c log base a of b. Now if you look, all I've just done is move this c to the side. So it's effectively become a multiplier. So if you look, anytime you have an exponent, you can just move it to the side and get rid of it over here. Why is this useful? Well, let's say I give you a problem that went like log, let's say 3, and I said 3 to the power 5. Well, you could use this rule, and you could move the 5 to the side. So you'd write log 5 log 3 base 3 of 3. And then you'd use this one, and if you look a and a, it's just 3. And remember, these would cancel to 1. So you'd get 5 times 1, which is just 5. Now, them 2 rules, they're more for understanding. You don't really need them, but they can help with understanding. Now, the second thing we need to understand is orders of magnitude. And orders of magnitude is just the difference between the indices. So if I gave you 10 squared and 10 cubed, do you see how there's a difference of 1? So therefore there's a difference of times 10 to the power 1. So we'd say it's 1 order of magnitude. Here we could also say, let's say 10 cubed and 10 to the power 5. Well, the difference is 2. So therefore it's times 10 to the 2, or 2 orders of magnitude. Now we can also find this information off of a log graph. So if we have, let's say, a log graph, we've got a line and this point and this point. Let's say that gives a value of 2, that gives a value of 5. Let's say this is a log 10 scale. Okay, well, what do you know? You know the difference in order of magnitude is 3. So there's a 3 order of magnitude difference. Now if you look up here, magnitude is just the difference in the indices. So therefore, because it's log 10, remember, log 10 means that the base is 10. There's going to be a difference of 10 to the 3. So therefore, the difference between this point and this point is times 1,000. Okay, so finally, there is one last formula you need to learn, and this is your final value is equal to your initial value multiplied by your growth rate multiplied by units of multiplied by time intervals. So write this. This is final. This is initial. This is growth rate, and that is time intervals. So for example, if I said that initially you have, let's say, I don't know, 20 leopards. 20 leopards, and I say that these leopards, they grow at a rate of, I don't know, let's say they double every 10 years. So double every 10 years. So therefore the growth rate is going to be 2. And if I asked you to work out the final number of leopards after 20 years, so after 20 years, of course that means that there's been 2 time intervals. Because remember, if one time interval is 10 years, then 20 years have got to be 2. So we stick a 2 there, and our final answer ends up as 20 times 4, which is 80. So after 20 years, there are 80 leopards. Now this was a worded example, so it might be confusing. So it's probably best to go over a few questions. Now there were no AQA actual questions, so I found this one on some American website, but it should do the trick. So the first question is, how many bacterium are present after 51 hours if a culture is inoculated with one bacterium? So the first thing we do is we write down our formula. So you write NT is equal to NO times GT. Now T is going to be 20 minutes, right? So T is 20 mins, okay? So 1 T is 20 minutes. Now it's asking us to work out NT, so NT equals. Now the initial number of bacteria is 1, so we write 1 times. The growth rate is of course 2, because remember they double. So every time they double, if they triple, then the growth rate would be 3. So we stick a 2 there. And remember T is time intervals. And it's told you it's 51 hours. So 51 hours, so 20 minutes equals 1 interval. So if we do 51 times 60, this should give us the number of minutes, and this works out to be 3,000. Wait, no, not 3,000. This works out to be 3,060. If we do 3,060 over 20, we get 153. So therefore T is going to be 153. Remember, there have been 153 20 minutes that have gone by. So NT is just going to equal 2 to the power 153, which is a very big number. It's 1.14 times 10 to the 46, But to be honest, it would just be better if you wrote it as 2 to the power 153. So of course that's a fairly simple one. You get your formula, you stick your values in, do a bit of calculating, there's your answer. The second one is the one where we have to use logs. Actually, I think it would be just easier if we just move the question. Right, so number 2. So how long would it take for an initial population of 6 to reach a size of 12,288? So again, we write that on the formula. So NT is equal to NO times GT. Now, it's asking us how long would it take. So therefore, we need to find this T, right? So let's stick in the values. So NT is 12,288 equals the initial. So the original population was 6. I remember they double. So if they double, the growth rate is 2. Okay, 2 to the power T. So let's rearrange that. If we divide both sides by 6, what we get is we get 2048 equals 2 to the power T. And this is where our log rules come in handy. So remember, we can take log of both sides. So log 2048 equals log 2 to the power T. Now if you remember our rules, so I've got to write a 2 at the bottom here. It's quite important to write that 2 at the bottom. So on the brackets. Right, here are the 2 rules. So the first one is log a to the a is equal to 1. Because remember, you're asking a to the power of something equals a, and that's 1. Second, log a bc is equal to c log ab. Remember, if ever we have an exponent inside the log, we can just move it outside and put it here as a multiplier. So we can do the same on this side. Let's leave this side alone. So we get log 2 2048 is equal to t log 2 2. Now if you notice something, we can now use our rule 1, where it's more like fact. If we use this, log AA is equal to 1, we've got 2 2. So therefore this cancels out and you get a 1. So therefore you end up with T is equal to log 2 2048. And if you stick that into your calculator, what you'll end up with is you'll end up with 11. So T is equal to 11. And we haven't actually finished because it says how long would it take. Remember, T is time intervals. So if you think about it, there have been 11 intervals, and each interval is equal to, so one interval is equal to 20 minutes. So therefore, to find the total time, we just do 11 times 20. And what we end up with 220 minutes. And so that is quite a simple example, but I don't really think in the exam they'd give you anything harder. But anyway, to summarise, you need to write down your formula, substitute values in, and then you rearrange using your log rules. Remember, these 2 are the important ones. So you rearrange. Once you've rearranged, you shove that into your calculator, you get your answer, and then you do whatever else you need to get to the end of the question. In this case, it was just simple multiply by 20, and you get the number of minutes.